Welcome back to our Algebra 2 series. Today we are up to section 5.5 where we'll be looking at exponential and logarithmic equations. This is a continuation of our discussion between logarithmic and exponential functions, where if we can say y is equal to log base a of x, we can also say that x is equal to a to the y power, where a is the base in both of these expressions. Today, we'll be taking everything we've learned in the past few sections and be solving actual equations, trying to solve for x. So let's start with this simple equation. 3 to the x equals 8. We can start by taking the log of both sides. In this case, we'll use a common log with a base of 10. And from previous lessons, we've learned that when you take the logarithm of an exponential expression, that exponent can come out in front of the logarithm. So log of 3 to the x can be rewritten as x times log of 3. Now we can divide both sides by log of 3. And we're left with x is equal to log 8 over log 3. Well, what do we do with these expressions? Well, if you remember, we have a choice. We can use a log table or just use a calculator. So for the time being, we'll just use a calculator because it's easier. Using a calculator, we can find that log of 8 is approximately 0.9031 and log 3 is approximately 0.4771. And that equals approximately 1.8929. And that's our answer. Here's a slightly more complicated expression. But once again, we can take the log of both sides of the equation. And again, on the left side, we're taking the logarithm of an exponential expression, which allows us to pull that exponent out in front of the logarithm. So we end up with the quantity of 3x minus 5 times log 2 equaling log of 16. I've made a point of putting parentheses around the 3x minus 5. We need to treat this as one entity. We don't want to mistakenly write 3x minus 5 times log 2. This is 3x minus 5 as a quantity times log 2, and there is a difference. And just like before, we can divide both sides by log 2. And we can add 5 to both sides. And once again, we use a calculator to find the values of log 16 and log 2. And they're approximately 1.2041 and 0.3010 respectively. If we divide those two, we end up with 4.003 and a continuing nonsense, plus the 5 that was left over. So if we add the 5, we have 9.0003 and a bunch of stuff. So x is approximately 3.0001 and some stuff. But we've been dealing with approximate here. Is it safe to assume that x is exactly 3? Well, let's plug 3 into the original equation and see what happens. It would be 3 times 3 minus 5 as the exponent. So it would be 2 to the 9 minus 5 is equal to 16. 2 to the 4 is equal to 16. Yep, that makes sense. 2 to the 4th power is exactly 16, so the answer is exactly 3. But it turns out there's a sneakier way we can do this. Going back to the original equation, 2 to the 3x minus 5 is equal to 16. The sneaky part is looking at the base of both sides of the equation. We've got a 2 on the left side and a 16 on the right side. 16 happens to be a power of 2. So we can rewrite 16 as 2 to the 4th. We have the same base on both sides of the equation with different exponents. 2 to some power is equal to 2 to some other power. But those two powers must be equal to each other. So we can simply say that 3x minus 5 is equal to 4. Or 3x is equal to 9. And finally, x is equal to 3, which is what we found the first time around. So in some cases, it's a lot faster and easier to be sneaky, so be on the lookout for these kinds of problems. Next, let's look at a logarithmic equation. Log base 3 of 5x plus 7 is equal to 2. Let's focus on the base of the logarithm and the result. So the base is 3, and the result is 2. Since we know that this logarithmic equation can be rewritten as an exponential equation, we know that the base of 3 to that power of 2 will be equal to 5x plus 7. So we can say that 9 is equal to 5x plus 7. If we subtract 7 from both sides, we get 2 is equal to 5x. And divide by 5, we'll get 2/5 is equal to x. And that's our answer. And here's a slightly more complicated problem. Log x plus log of x minus 3 is equal to 1. Using your brain and your eyeballs, let's look at this logarithmic equation. Because the base isn't written, we know that it is base 10, or a common logarithm. We can also see we're adding two logarithms with the same base together. That should be a clue on what we need to do next. Because we're adding two logarithms together with the same base, we can rewrite it as a single logarithm with that base of two things being multiplied together. If this seems like wizardry, go back and watch section 5.3, where we learn that if you take the logarithm of two things being multiplied together, here x and x minus 3, they can be rewritten as a sum of two logarithms. So again, let's focus on the base and the result of the logarithm. The base is 10 and the result is 1. So we can rewrite this logarithmic equation as x times x minus 3 is equal to 10 to the 1 power, or just 10. If we expand that, we get x squared minus 3x is equal to 10. Subtract 10 from both sides to get x squared minus 3x minus 10 equal to 0. Now we can use our old powers from algebra to factor this into two binomials, x plus 2 and x minus 5. So to solve that equation, x is equal to negative 2 or x is equal to 5. But we have a problem. This negative 2 is a problem. What happens if we take this negative 2 and put it back into the original equation? Let's use a calculator for that. What is the log of negative 2? Calculator doesn't seem to like that very much. And that is because negative numbers don't have logarithms. If we take a quick look of the graph of y equals log the x, you can see that it is only positive values. It's impossible to take the logarithm of a negative number. So going back to our original equation, we eliminate x minus 2 as a possible solution. So the only solution is x is equal to 5. Let's jump over to the whiteboard and do some examples. All right, we're going to start with something very simple. We're just going to say 2 to the x equals 7. So we want to solve for x. But to do that, we want to get it out as an exponent. So let's start by taking the log of both sides. And we'll do a common log. We don't need to write 10, but the base is 10 here. Log of 2 to the x equals the log of 7. Because we're taking the logarithm of an exponential expression, this exponent can just jump out front, which is very handy. So this would end up being x times log 2 equals log 7. Then we just divide both sides by log of 2. These will cancel out and turn into a 1, so x is equal to log 7 over log 2. And we'll use a calculator because we're lazy and find that the log of 7 is approximately, and I'm going to make this an approximately because we are kind of cutting off some decimals here, 0.8451. And the log of 2 is 0.3010. And if we divide these together, again, we're in approximately land. This is 2.8076 and some other stuff. And I took up more space than I was planning, but let's clean this off and do an example. This time around, we're going to do 4 to the 2x minus 3 equals 64. But this time, we're going to be sneaky about it. 64 is a power of 4. 64 just happens to be 4 cubed. So let's just rewrite this as 4 to the 2x minus 3 equals 4 cubed. 4 cubed is 64. So now we have an equation here where we have 4 to some power is equal to 4 to some power. So these two expressions up here, these two exponents, have to be the same. So we can get rid of all this exponential mess and just say that 2x minus 3 is equal to 3. If we add 3 to both sides, 2x is equal to 6. Divide both sides by 2, we get x is equal to 3. We're going to jump over to a logarithmic equation and see if we can't just squeeze it in over here. We're going to say that the log base 5 of x is equal to 3. Now remember, just the basis of this can be rewritten as an exponential equation. The base is 5, 2, the resultant of this is equal to the inside of the logarithm. And 5 cubed, well, that's just 125. Pretty easy. Let's clean this off and do one more final bonus problem. All right, let's make something a little more complicated. We're going to have the log of x with no base written, so it's a common log, plus the log of x plus 3 is equal to 1. So again, we have two logarithms being added to each other with the same base. So we're undoing that thing we learned a few sections ago where you take the logarithm of a product. So we know there's really a product hidden in here. So we can rewrite it as the logarithm of a product. The two things being multiplied are x and x plus 3. So it's a logarithm of, and maybe I'll just use square brackets to kind of keep it a little more clear, x times x plus 3. We're taking a log of two things being multiplied together, x and x plus 3, that can be rewritten as a sum of two logs. So we're kind of going backwards from what we learned a few sessions ago. And this is still equal to good old 1. And now we have a single logarithmic equation. Log base 10 of some stuff is equal to 1. So that base of 10, and again, there's a 10 here, 10 to the resultant, which is 1, is equal to the stuff inside the logarithm, x times x plus 3. And we got a little more room over here. Let's expand this into x squared plus 3x. And 10 to the 1, well, it's just 10. And we'll just write over here for fun. So looking at this here, I'm going to subtract 10 from both sides of this equation and try to give myself a little more room. X squared plus 3x. We're going to subtract that 10. It's equal to 10 minus 10, which is 0. That burp was clipping burps. So now we go back to our good old algebra days and see that we have a polynomial that can be factored. So this turns into two binomials. We're kind of unfoiling, right? Equals 0. We're going to have an x and we're going to have an x. So we have a minus sign here. So we have a plus and a minus. We're going to have two things that multiply together to make negative 10, but add together to make 3. So that ends up being 5 and 2. Let's just check our math here. We'll have a 5x here and a negative 2x here. That gives us 3x. And 5 times negative 2 is negative 10. OK, so we have unfoiled this polynomial correctly. So that gives us two possible solutions to this equation. We need one of these two entities to equal 0 for the whole thing to equal 0. So if x was 2, 2 minus 2 would be a 0, and we turn everything to 0. So one possible solution is 2. The other one would be negative 5. Negative 5 plus 5 would make this 0, make everything 0. So x equals negative 5 is the other solution. But this should be setting off warning bells in your head. Because if we took this negative 5 as x way back up here, we would be taking the logarithm of a negative number and the world would explode. So we have to eliminate this as a solution. So in this case, we have one solution. X is equal to 2. That's it for today. We'll see you next time.